And share screen. So yeah, I updated these pages. And by the way, if you haven't looked at the exam page, here's how I adjusted it, because I was gonna have 20% for each exam. So I just decided to make basically 40% be the higher of the two scores and 20% be the lower. Figured that was the nicest way to do things, least stressful. So, and yeah, we were supposed to have this like note-taking thing, but I never really was able to make lots of videos. So I'm just give you all full credit for like the 3 videos I made you watch. Okay, so there's that. And then, like I said, the final exam, we won't have the closed book part like we did before. It'll just be like the completely open. I'll post it next week, and then it'll be due the fall. I think our exam is scheduled for the Thursday, like our official time on the registrar's site is next, so that's what I put the exam due. And I'll put a bunch of office hours and stuff. Okay, so you can just check that online. And oh, I need to post the problem set, but like, yeah, so I didn't want to make you guys have to do a problem set like do tomorrow, so I'm just gonna have a problem set due Friday and then next Tuesday. And that's it. Are we cool? Sounds good? Any questions? No? All right, that's good. Oh yeah. Yeah, kind of similar to what you did on the first exam, right? Yeah, I'm just looking for kind of the same thing. Yeah, okay. Let's see, so then what else are we doing today? So I guess what we're doing is math. Let's do some math, shall we? Here, maybe I'll put a picture on the screen just to entice you. We'll get to it later. But it's just gonna open it now. Yeah. This is a very exciting picture, I know. Just imagine what kind of amazing math we're gonna do based on this picture. Okay, so today, so we have 2 weeks left. We have six classes left together. Oh my God, OMG. And we need to do line integrals. That's kind of the last big push, last major topic of the course, are line integrals. And so I got to tell you what a line integral is. And the book jumps straight to these integrals that are like called like work integrals. Like the analog is going to be the physics concept of work. But I do want to give you a little more general idea and definition, because it does go beyond, I mean, sort of all the cool theory and like physics related stuff involves like integrating vector fields along paths, which is what that picture is supposed to somehow be thinking about. But in general, let's just say we have a path C. I should say an oriented path. Oriented, which means it has a direction. In the plane or in space, I'll just say in 2D or 3D. How many? Oh, there's an eraser. Okay. In 2D or 3D, and a function f f of x comma y or f of x comma y comma z, depending on whether the path's in 2D or 3D, defined along C. Okay, so now I'm just going to draw a 2-dimensional version of this. So like, so say we have, this is our path C. And at each point, you know, like say this is the point, let's just x naught comma y naught. Then we could actually plug in f we could plug in f at any point along this path, right? And get a value of the function. And I want to somehow integrate, like, I guess maybe I'll just put this in quotes, like integrate f along c. If you think about single integrals, what you did before multivariable calculus, we integrate along a path on the number line, the path just from point A to point B, right? So it's kind of like, but you know, there's those rules like on the number line that if you like, you know, you integrate from A to B and then from B to C, then you can actually do like the integral to B minus the integral from, or actually plus integral from B to C because it would be negative because it would go, you know, so you can actually, it's sort of like following a path also. It's just a one-dimensional path, so it's dumb that we don't really think of it that way. So I'm just trying to like give the analogy. But so how do we do this? Well, okay. Let's use the Riemann sum idea because that's kind of where everything comes from. I think that's the easiest way to see what's going on here. The Riemann sum concept, which is we're going to actually break this path up into pieces, or maybe like I pick, you know, pick points along the path, and then I could think of sort of saying, okay, well, I mean, what do we do? Again, think about the analog in single variable integral. The Riemann sum idea is we break up the number line into these pieces, right? And then we sort of, let's say we do like a left sum or something, right? Remember the idea is there you use the left endpoint of each interval to make the height of your rectangle, right? And so it's like, you know, this is delta x, and this height is like f, given by f, height f of x. And then it's just base times height, base times height. That's kind of how you do the integral, right? So I'm gonna do something similar here. And the way to think about this, I guess, is like, well, I almost want to approximate this by straight line pieces. Right, so break the path into pieces, approximate the path by line segments. By line segments. So let's just call these something like, well, okay, the thing I'm going to actually use is delta R. So that's delta R1, delta R2, and this is the length. This is going to be the length of the path of the line segment, and so on. Actually, sorry, I should call this 0 probably from, well, actually, let's just do 1. Maybe I'll do a right sum. Okay, delta R3 up to, so this is delta Rn. I'll write down what that means in a second. And then this is the point xn comma yn. This is the point x1 comma y1, et cetera. Right? Where delta Ri, it represents the length of the line segment. Of the line segment from, I guess the way I set this up, xi minus 1, yi minus 1 to xi, yi. Does that make sense the way I set it up? Delta R1 is the length of the line segment from x0, y0 to x1, y1, et cetera. I'm not worried about being, I mean, I'm sort of just trying to be a little bit careful here, but it's going to be, you know, you write down the Riemann sum and then you turn it into an integral. So, and then the Riemann sum then a Riemann sum, I guess I'll say a Riemann sum because it could be right or left or however you want to do it, is something like f of x1, y1 times delta r1 plus f of x2, y2 times delta r2, right? Up to f of xn, yn times delta rn. I'm trying to do this just the exact analog of what we do with single variable calculus, where I'm basically doing a base times a height or something like that, but it's like the base is the length of the path. It's sort of trying to approximate the length of the path and break it up. Does that make sense? Yeah, Iman. xi yi to xi plus 1 yi plus 1 instead of, yeah, so I think just the way I set it up and the way I labeled things, but if you label things differently, this could be from xi yi to xi plus 1 yi plus 1. It's the kind of thing where I'm trying to do it kind of the right way, so I'm setting up the Riemann sum, but then when we go to the integral, we're not going to care about the indices and stuff. So, but right, so this is the sum xi yi times delta ri. I guess here I did I equals, I think this is the analog of a right sum, because I'm using the end of each line segment to evaluate, right? And that's summation notation. You guys remember? Have we used summation notation in this class? I can't remember. We did? Have we? I don't know. Anyways, so, okay. Now the question is, if we wanted to actually do this, if we wanted to sort of let n go to infinity to turn it into an integral, right? We let n go to infinity and then we'd pick more and more points along the path. We get shorter and shorter line segments. It's nice because we're approximating the path better. Places where the path is curvier, the line segment's not approximating it very well. So to get integral, let n go to infinity, delta ri go to 0, right? And then we'll get something like, actually, let me give these points names. Let's call this the point A, and this the point B. So this will be something like the integral from capital A to capital B of f of xy dr, right? Again, just kind of like purely formal nonsense going from a Riemann sum to an integral. The problem is like, don't really know, like if you just sort of look at this, you're like, wait, how do we actually compute this, right? Like to do the delta ri, we would actually need the distance between two consecutive points. So we need like the distance formula over and over again and stuff like that. So how do we actually compute, or how does we even make sense of this? Actually compute one of these. Because it's going to turn out that we're going to piggyback on single variable calculus just like we've done with double and triple integrals. Okay, so what I want to do is I actually want to define, I want to draw the path again. Sorry, can people see the screen? Or see what I wrote up there, kind of. I guess the screen's kind of in the way, but all right, yeah. Okay, so I want to draw the path one more time. This picture's getting kind of, I want to think about the delta ri a little bit differently. And really what we want to do is use our vector knowledge, right? Because what we're gonna need to be able to actually compute one of these is we're gonna need to have parameterized the path. That's really what we're going to need to do. That's why we talked about parameterizations. So how to actually compute one of these? Let me draw this again. Here's C. Here's the path C from point A to point B. Let's say C is parameterized by R of T, where A, remember, so okay, I know it's been 10 days, but hopefully you remember what I mean by this. Like, we had examples like for the unit circle, like if we had like the unit circle, or if I just wanted like the first quadrant of the unit circle, that would be, you know, cosine of Ti plus sine of Tj from T going from 0 to pi over 2, right? Just trying to remind you, this is what I mean, like, right? This is how we write down an actual path as we parameterize it. And then we have this T parameter. Okay, so now, if you think about that, point capital A is really what in terms of this? Beginning of the path. R of little a, right? So that's R of little a. This is R of little b, right? If we still have our points, if we still have our path broken up, maybe I'll just do it as fewer points to make it more stark. If we still break up our path, like, you know, this is x0, y0, this is x1, y1, et cetera, then this could be something like R of T1, right? Like a specific T. And then this point all the way at the end could be like xn, yn. Well, I guess it's R of B, but it could be R of Tn, and this could be R of T2. So you get all these points, right? So now what delta R is it's actually the length of a vector from one point to another. So what we really have here are a bunch of vectors. We got to use our vector ideas here, right? So really a bunch of vectors. Something like this could be the vector delta R1, but like a vector, right? So where delta R1 means, you know, R of T1 minus R of TA, right? It's a change. It's really like a change. Like you're using, again, like I have the like infinitely stretching arm that can like trace out this, and then my arms my shoulders at the origin, and it's tracing this out. And really it's like the difference between the two is, between this point and this point is just the difference of those two vectors, right? And then delta R without the arrow over it, delta R1 is the length of delta R, one like that. So basically, yeah, we've done that before sometimes, right? Where it's like, we sort of represent a quantity, a magnitude of a vector by just without the arrow over it. Does that make sense? Okay, now the question is, what happens as delta Ri goes to 0, right? Like we want to actually get an integral. We have put things in terms of a parameter now, which is good because it's starting to feel more like we could do this as a single integral, like somehow integrate, and what we're going to integrate is going to be a t, because we're going to put everything in terms of t. So yeah, so what happens as delta Ri goes to 0 in terms of vectors? Well, okay, so what we have is something like, let's just look at this example of delta R1, right? Wait, what did I write here? That's a 0. Oh, I went to write A, but that's also T sub 0 or something like that. So, okay. So for example, yeah, I mean, I'm actually gonna call this like T sub 0. We could call this T sub 0 and T sub 1, or T sub n. We do this a lot when we do Riemann sums. We label the endpoints as like special T values, right? Okay, so as delta R sub I goes to 0, that's always the problem with integrals, right? With Riemann sums, is that you're really doing like, you're trying to let something in the sum go to 0, and you're really multiplying 0. You're adding 0 infinitely many times, and somehow that's supposed to make sense in the limit, right? That's kind of what a Riemann sum is. But in terms of vectors, let's just look at something like this. There should be something that looks sort of familiar to you. If I think about delta t, right? Delta t, these could be like at different, this could be like, remember, we sort of label the points on a parameterized curve by the parameter. So I could have t equals t1 here. This could represent t equals t2, et cetera. So delta t would barely be like the difference between two consecutive t's. So in this example, it's like r of t1 minus r of t naught over t1 minus t naught. Does that look like a familiar quantity to you? What does that look like? Yeah, same thing. Yeah, this is actually an average rate of change. Yeah, but like as T1 and T naught come together, this goes to the derivative, right? So this goes to like, there actually is a sense of R prime at say like T naught. Like imagine making delta T smaller and smaller, so T1 is sliding along this towards that, right? And so there's actually a sense here of like the derivative of one of these. And so what delta R1 really is, when we want to go from, when a Riemann sum, we go from delta to D, delta R to dr. Well, basically what we're saying is delta R1, and I'll give an example in a second because it's kind of abstract. This is approximately dr dt. Well, it's really, I guess actually it's the magnitude. I should be careful. This I should put an arrow over, sorry. Yeah, I don't want to use the magnitude, but this is really dr dt, which is r prime of t. What is the derivative? We can differentiate. We didn't actually talk about this, but in this example, there's no reason you couldn't differentiate this. It's derivative of cosine. Is it negative sign? If we differentiate, we get that. But what is that? Like, what is r prime of 0? What's r prime of 0? Yeah, it's 0i plus 1j, right? So that's 0i plus 1j. So actually, an r of 0 is right here. So which way does r prime of 0 point? Like that. Which way do you think r prime is going to point, like at this tangent? You could check. You could put in pi over 4. It turns out that this vector is tangent to the path. This is actually a tangent vector. Yeah, we didn't talk about this, but, and you can sort of see it because it's actually like, it's like the delta is like the vector from point A to point B. And as you slide them together, it's kind of becoming, it's getting shorter and shorter, but it's becoming like a tangent vector. right? Because it's following the path more than. Okay, so the thing I really want to say is that dr, oh, just covered that, sorry. Dr, we're going to really write that as r prime of t dt. That's really what the dr is going to be. It's almost like a u substitution or something where we've like written r in terms of t and then substituted. You know what I mean? Sort of looks like a u substitution kind of. So that's the big thing. And then so the magnitude of dr is just the magnitude of r prime of the tangent vector dt. So sorry, I'm gonna end up covering this up, but so dr without the arrow over it is the magnitude of dr is the magnitude of r prime of t dt. And so if you want to actually talk about this integral now, we could think of it as like this integral right here. I'll write this again. Then the integral from point A to point B of some function, and I'm just doing a 2D function dr, we can sort of do this substitution and really turn things into be in terms of t, right? Like in this, sorry, let me pull the board down again. This right here is like x of t, y of t, right? We can also think of the path that way, like x and y are functions of t. And so when we rewrite this, we can think of it as from little a to little b, f of, like these are functions of t really, so we can get everything in terms of t, times the dr, which is this thing, times the magnitude r prime of t dt. So I could really use the parameterization. We can actually use the parameterization to get something that we can integrate. Like if you plug in everything in terms of t, you'll get a function of t dt. It might be ugly, but you'll get. In fact, one reason we don't do a lot of these, I'm going to show you these specific work integrals, is that here, if you really wanted to compute using this would be like the square root of x prime of t squared plus y prime of t squared, right? The magnitude of the derivative. By the way, if you've ever done arc length formulas before, you do that in single variable. Some people do that in single variable calculus. You might have seen something like this, where there's like a 1 plus dy dx squared square root, if you want to find the length of a path. So this is actually a generalization of stuff you might have. If you haven't, it's fine. But so it is possible, i.e., I guess the upshot here is that it's possible to integrate as long as we parameterize the path. So to integrate function along a path, as long as we've as long as we can parameterize the path. That's sort of the in English version of this. Okay. So it's, right now it would be like, let's do an example, but actually, maybe I should give a quick example. I just thought I was going to just move on to because this is usually kind of hard, but actually the example, well, the screen's now covering up with the circular arc. let's do the function x times y on the quarter unit circle. In the first quadrant, the one I drew. So really we have, so C, let me just draw it again. So C would be like this. That's your C, right? And like we said, R of T is cosine Ti plus sine Tj from 0 to 2 pi. I'm pi over 2. We're just doing the quarter circle. R prime, this is a nice one because the magnitude of R prime is nice, right? I'm just copying this from what's covered on the board, what's covered up by the screen. What's the magnitude of R prime? Yeah, sine squared plus cosine squared, right? Square root, which is 1. Magnitude of R prime of T is 1. Always, that's nice. It's not usually that nice, but it's nice in this case. And so really, if you wanted the integral, this is from point A to point B, right? I think I could probably fit it here. That the integral from point A to point B of x, y, dr, that kind of looks weird. We're trying to keep in mind that this is not, it's not a dA, it's not an area, it's not a double integral, it's a path integral. Or if they're called line integrals, they really should be called path integrals because not all paths are lines, but what we can do basically is we can just write everything in terms of, right? We can write this as the integral from 0 to 1 to pi over 2 of x of t, y of t, magnitude of r prime of t, dt, right? That's kind of my point up there, like, or I guess what's covered now by that. And then this is easy because x is cosine and y is sine. So this just, and then this is 1. So this just ends up becoming the integral from 0 to pi over 2 of cosine t times sine of t times 1 times dt. And that becomes something you can integrate. Does that make sense? Again, there's a question of like what this would even represent. And there are ways to think about this, like, again, our books doesn't go in this direction as much, but like, if you think of this path lying in the xy plane on the ground, and you think of the surface x times y above it, then you could imagine like a curtain, kind of like all the points. Like if you have this path, like the path on the ground would go up to a path on the surface. And then everything between would make like a curtain. And then it would be the area of that curtain. I'm not even going to draw it because it's not even what we're going to do. We're going to calculate in this course. And it's not calculated that much, but it's interesting, the idea that I could have some weird curtain in 3D and I could actually calculate the area of it. You do something like this. Okay. But the thing that where we go with this actually is in this direction of these. We integrate a path, a vector field along a path is what we're going to do. And so now if you go look at the screen and imagine that we're in some, share this for a second. We're in some vector field where the arrows are all like going around like this, and then you follow some path in the vector field. Then you can imagine that it's like a work energy kind of thing of like the path, like the field, if it's like a force field that it's carrying you from this point to this point, that it's, it's pushing you, but you decide to follow this path. I mean, there's paths where you go, like this one goes against the field, for example. So you could go against the field. Although, so the field will end up doing negative work on you if you go this way. But I need to write down how this is actually going to work because it's a physics concept of work, but it really comes up in lots of interesting physical applications. So let me just, yeah, and these slides are on the handouts page. Okay, so but I kind of wanted to give the general idea that like you can integrate any function along any geometric object just by doing a Riemann sum and figuring out how to actually like turn that into an integral. That's kind of was the point of that whole discussion. Hopefully that was somewhat compelling. But then, yeah, the specific example we're going to do, which is going to actually become computationally easier because that absolute value, or not, the magnitude of r prime of t could be really annoying to compute if you actually had functions. Like we got something where the magnitude was 1 the whole time, but if you actually had functions under there, you get something very annoying that really you would just ask a computer to approximate. But it's going to turn out when we do these sort of path integrals, these sort of work integrals, that they're going to be easier to compute because something nice is going to happen, which you'll see in a second. So now we have an oriented path, oriented curve, C in 2D or 3D, and a vector field. We were talking about these vector fields just before break. F, and it could be, you know, x comma y or x comma y comma z. I guess it's kind of similar to what I was writing at the beginning of class. Right. And now, so if a particle follows C, from beginning from point A to point B, what work does F do on the particle? Right, that's the question. So remember what work is. This is kind of physics, you know, reminders, but work is force times distance, right? Like if you apply a force through a distance, that's an energy. The units are energy, and that's called the work. So let's remind ourselves about work. Work is force times distance. Like for example, if we lift, you know, like a 5 kilogram block from height 0 to height 10 meters or something, right? Then the force, the gravitational force, is mass times gravity. So that's 5 times 9.8 newtons, right? Newtons, which is, I guess, kilogram meters per second squared because mass times acceleration. And then the work is F times D, which is this Newton meters, 5 times 9.8 times 10 joules, which is Newton meters. Newtons is kilogram meters per second squared. Joules is Newton times meters, or I guess kilogram meters squared per second squared. Anyways, so, right. That all sound kind of familiar from some point in your life? It's not a physics class. It's about all the physics I know right there. So I just kind of wanted to remind you of this. And so so we would actually do something like that. What if we wanted to move this, like I'm saying, raise it like that, right? What if we wanted to move it along like an incline or something, like push it up a ramp? what happens there? Does the work change? The total amount of work changes if we lift it to 10 meters. Well, this becomes a physics problem, but. Oh, right, a frictionless ramp or something, I guess. That's interesting. Okay, but if I just moved it horizontally on a frictionless surface, that would be no work, right? So there's a reason I'm saying this, which is really like, how do you compute the force times the distance? Because the distance is longer, right? Well, it's more like what's the force then? So this is sorry, let me just draw this a little better, because that's going to be an important point for like how we're going to do this. But like, okay, so let's say we have a ramp, just like 45-degree angle ramp, h equals 0 to h equals 10 meters, and the force is really like a downward arrow, right? The force. So here's our block, 5 kilograms. The force, gravity is this downward force, which we said is 5 times 9.8. I know that's, what is that, 49, I guess, but I just gonna keep saying this 5 times 9.8. If we go this way, I mean, this is actually really, I guess I should say there's a negative sign here. I really kind of want a negative sign here because we're going against gravity. We're doing work, but it's going to turn out that we're going to think of this as the field doing negative work on us. Gravity. Field does negative work. You're too self-centered, thinking about it from your perspective. It's really just nice to think about you're going against the arrows. So here the arrow would be going the direction of the travel. It's almost like this is C1, and this is like C2, right? So they're two different paths. And so constant forces along straight line paths, you can actually do pretty easily. You don't really need calculus to do that, right? But let's think about this. So this is our path C2. There's a force vector at every point. But it's always pointing straight down. So how do we actually figure out? Yeah. So you do cosine to get the horizontal, or wait, the force that's actually down, you're saying? Yeah, okay. So it's interesting. So like we have, let me just like take these out. We have this, which is our direction vector, and this, which is our gravity vector. And we really want the component of the force in that direction, right? And so these are 45-degree angles. And so I think you're multiplying by, yes, it doesn't matter here, sine or cosine of 45, just depends on how you set it up. But it's like this is kind of what we want, right? So the force to go up at any given point that we need is we're going to match the, it's, if you have a long ramp, again, think frictionless, you don't need as much force to push at any given moment to push the block, right? Like lifting it straight up would take more effort than just like pushing it along the ramp. Okay, there's a point here, there's a point coming here, which is going to be related to what we're doing. But So the force I'm claiming is actually, or to counteract gravity, we need a force, like a force vector that's sort of canceling out the force vector. Well, we're trying to push it along this direction, right? And it's going to need to cancel that. And so the force, the upward force is going to be like that, which is actually whatever. Yeah, this is getting to be too much of a. Yeah, actually, I guess what I'm really trying to do, sorry, physics is, I'm bad at physics. Let me try to draw this again. I was always bad at, even in high school physics, I was always bad at drawing these diagrams. We basically want to take the force vector opposite, right? And then we want the component. What I really want to do is think about dropping, I think that thing that was, and I think probably what you were saying was right. I want to think about this. This is really the component, like the direction, right? That's really the vector I want for like the force to counteract. And so that's a 45-degree angle. Yeah, I was looking at the wrong triangle. And so this is, let's just say this is mg, or the magnitude of the force is mg there. Then this, the magnitude of this is mg cosine 45, right? That's what you were trying to say. Okay. So that's actually, because it's a less of a force we would need to counteract gravity if we're pushing it up a ramp, right? Times distance. What's the distance of, so we need force times distance. Work is force times distance. Here we get mg cosine 45. And now what's the distance? It's 10 root 2, right? Is the distance of, it's the length of the ramp. Yeah, pushing up, push up a ramp. That's what I'm, sorry, in your notes, it might look kind of random, but. Okay, so what happens? You see what happens mathematically? What happens? We get the same thing we got before, because this is 1 over root 2 and that's root 2. These actually cancel, and we get mass times gravity times distance. Times the original vertical distance, right? Same as before. So there's a couple of things that are interesting here. Gravitational field is actually called conservative, which means it doesn't matter what path you take, you do the same amount of work. Like if I climb out a window and climb down a ladder to the first floor versus going down the stairs, it's the same amount of work total that's done. Same amount of force expended. If I lift this block straight up versus I push it up a nice shallow ramp, that's sort of easy. Again, think frictionless. It's pretty easy, but you need some force to do it. But the total amount of work is the same. That's the first thing. The second thing is we only care about the component of the force in the direction. Okay, so yeah, points. So the gravitational field, this is going to come up later. Field is conservative. Doesn't matter, sort of, there's another term for this, which is sort of like path independent. Doesn't matter how we got to height. 10 meters. And the second thing is use the component of the force along the path. Right, that's what we're using when we compute. And that was what this whole like times 45 degrees thing was. And what we want to do, I guess we're gonna have to do this next time, at the beginning of class next time though. If we want to do these an actual work integral, so to find, let me just say this kind of briefly in words, and then we can do the math on Wednesday. To find work along a potentially curvy path C, the work is going to be the integral. Actually, one thing people say, which I didn't write before, is just C, but I'll just do A to B. A to B, and the function, it's the dr here, and the function is the component of the work tangent to, component of the force tangent to C. That's the function we're going to be integrating. Right, this is the function we're going to integrate. And the question is like, how do we actually write this down? And it turns out it's going to be quite nice. This is the function. So next time we'll see how to do this. Okay, like I'll just kind of like preview. It's the kind of like a nice thing that happens with the math that lets us actually be able to compute these. But that's kind of the abstract idea. Sorry, we ran out of time. Okay, thank you everyone. I will post the problem set as soon as possible. Due Friday. If I don't, at least one person in this class will yell at me. Does she know who she is? I'll post it, yeah. All right, take care everyone. Let me stop.